the next thing I wanted to talk about how to do is how do we find a trend line or a line of best fit, a linear equation which will help represent the data or which is useful for prediction. Often this is called least squares regression. The process of actually finding this line requires us to minimize the amount of residues from the mean, basically. But if you follow the process from our book here, basically you can use, if you have calculated the correlation, you can use the correlation to figure out the slope of your best fit line. And another basic principle of the line is it should always pass through the mean. So like kind of recapping through our data here, Amanda's mean time spent studying for her quizzes was 3 hours. And her mean score on those quizzes was an 87. Basically, the line of best fit should pass through that, and its slope is determined by the correlation in order to best fit the rest of the data. Basically, as our book says it, the least squares regression line is the line y, and they use this little hat with like a little caret above the y for always for regression lines or predictive lines. And it says equal to a plus bx, or basically a is going to be the y-intercept of that, and b is going to be the slope. Usually it's written in a math textbook as mx plus b is a more common way of representing linear equations. And this notation is a little confusing because they're using b for their slope instead of their intercept and a for the intercept. It doesn't really matter what we call it. I just wanted to warn you to be careful because b is actually going to be the slope of our line as it's stated above, and the intercept will be a. But what it says is the slope of this line will be equal to r, which remember r is the correlation, multiplied by the ratio of the standard deviations. And we've actually calculated all this. So all the math that we've done means that we can actually figure out the slope. I'll just write slope is equal to b, which is equal to r. So we found r to be approximately 0.929 multiplied by the standard deviation of the y variable, which we had that up here. So S sub y was 15.64 divided by the standard deviation of x, which was 1.555. And all of this should give us our slope of our regression line. And notice how, if you're wondering how would we remember such a formula, notice that the ratio of standard deviations is done y to x, because that's how slope always works. Slopes is always done in a rise over run process, where it's like how much does the rise, affect the run, and that ratio determines the steepness of our slope. The correlation tells us how much that relationship holds true, and if we divide the standard deviations, that's kind of a not a super in-depth look about why the slope comes from there. But that might help you remember this formula if you ever had to memorize it for whatever reason. So if I take that and multiply by the standard deviation of x, or of y, 15.64, and divide it by the standard deviation of x, 1.555, that would give us a value of approximately 9.34. So 9.3. I'll go ahead and just write and notice how I use the squiggly equal signs, or sort of like with tildes, to indicate when I'm approximating the value of something as opposed to doing it exactly. But we have a slope of about 9.34. And then our y-intercept, again, those are important for determining the equation of a line in algebra, which is said to be a by our book, which would be equal to, and basically once I know the slope of a line, this is another general principle. If I know the slope in the equation, I could always find the y-intercept by plugging in a point. But since we're always assuming that the mean is along the line of best fit, notice how that's exactly what it says. The intercept is equal to y bar minus b times x bar. So basically, if you're plugging in the mean into this equation, and remember x bar and y bar, those just mean the mean. Basically, you take the y mean, we know her mean test score was 87, and you subtract away by the slope times, which we just found to be about 9.34, and that multiplied by her mean time spent studying, which was 3 hours, I believe. Let's double check. Yes, x bar. But basically do y bar minus the slope times x bar. This will give us the appropriate intercept for the equation. So 87 minus, I'll just use the answer because that's more accurate, times 3. And this would give me a y-intercept of approximately, again, I'm going to use the approximation because I've been doing a lot of rounding throughout this process, 58 point, let's just say 59. It's a close enough estimate to that if I round to the nearest tenth. And there we have it. So that means my equation is y is equal to the slope times x plus 59, or mx plus b is a more common way of representing those variables. But this would be our least squared regression line. We'll actually use Excel at the end of this module to see how accurate, how good did we do in this. Did our rounding actually cause any error? And actually, let's before I end this video, let's actually finish answering the questions. It says use your line to predict Amanda's score if she spent only 1 hour studying, and check your answers in Excel. Graph on your scatter plot from question 3. So if we go back to our previous question over here, if we actually graph this line on top of our data point, basically what we are concluding is that our y-intercept should be at 59. So let's graph our trend line here in red. And then it should have, so basically the y-intercept should be right about here for our trend line, 59, and it should have a slope of 9.34. That just means that every time I run one, I should rise by 9.3. So just approximating what that would look like, it'd be something around there. Also because that's about 9.3. Again, it's kind of hard because it's, I'm starting at 59 and I should be going up to roughly 69, but it should really be more like 68.7. But I can't really be that accurate with this graph. It's just doing an estimate of where this line would be. But it should also pass through the mean, which would be the 0.3, 87. So I might as well graph that. That would actually be a little bit of an easier way to create this line as well. So if we know the intercept and we know the mean, you can always just connect those 2 points to graph the least squares regression line. So let me use a straight edge to try to create a straight line here. But if you just use like a piece of paper or a ruler, this can help. Actually, my iPad doesn't like it when I put a piece of paper on it. Doesn't seem to let me draw on it, but again, just doing my best estimation of what this line would look like. And remember what I said in class is usually roughly half the data is above the line, roughly half is below. It kind of depends on if there are any extreme outliers, but this seems about right. I can see that some of the points they're all pretty close to this line. It seems to pass the smell test. And also using the line, another point of this is we now have a predictive pattern behind if she spends X hours studying, her score will be Y. Now again, this is not exact, it's not an exact science, but it gives us an estimation for what will happen. So the other question it asks us is to use it to predict Amanda's score if she spent only 1 hour studying. But if we're looking at our line, basically we can kind of see on this line, well, if she only spent 1 hour studying, we'd expect her to get a fairly low score based on this least regression line. And of course we could actually use the formula and we could plug in 1 hour into this just to see what her score would end up based on our model here. So her score is y, which would be equal to 9.34 times x, which is the time she spends studying. And so we'd expect her to get a 59 plus 9.34, which is approximately a 68.3% on her quiz. So basically, she can expect to get a fairly poor score based on her regression in this particular case.